Hello everyone and welcome to Physics Rich once again. Today I have brought to you another playlist and that's the Awesomeologist playlist. Do you guys know about ophthalmologists? A little bit of wordplay over there. Ophthalmologists are doctor of eyes, but we are going to be Awesomeologists. We are going to be doctors of awesome things. What is that awesome thing that we are going to learn today? So guys, we are going to learn about the applications of Bernoulli's theorem. This is our topic for today, the application of Bernoulli's theorem. Now, you guys know that Bernoulli's theorem is central to the understanding of fluid mechanics. This lecture, I'm going to keep it small, is going to be useful for the preparation of JEE mains and advanced and NEET alike. Although I have titled it for JEE only because the kind of twists and turns that JEE puts in fluids and basically physics everywhere is somewhat more than NEET. So this is going to help you guys alike. If you are a JEE aspirant, NEET aspirant, AP aspirant, all of you guys can benefit from this lecture. So let's get started. So let me present to you the first question that we are going to discuss today. I would like you guys to pause the video and read the question, and then I will begin the explanation. Pause the video. All right, let's go. So what is happening over here? You see that there is this tube, all right? Please do not make the mistake of thinking that this tube is vertical. There's no gravity acting downwards. There's no gravity acting downwards, okay? Let's be clear with that. There's no gravity. So what kind of a tube is this? This is a horizontal tube, okay? It's on a level surface and it is bending like this. I hope you get it. It's bending like this, okay? It's an L-shaped tube, like a curved L, but it's not like this. It's like this, okay? Now he's asking you that if I mark these 2 points, 1 and 2, at which point do we have a greater pressure? And he's also asking us to draw the shape of the streamlines. So lots of students, in my experience, go through confusion in this problem. And I want to end the confusion once and for all. Let's see what is happening. We see that fluid enters over here and exits over here. But we do not exactly know what's happening over here. So, you know what? Let's do one thing, which is the most obvious thing, which is to break down our problem into tiny parts. And in this case, let's break down our fluid into this small, tiny part. You see this small, tiny part, it has a very tiny volume dV, okay? It's got a tiny volume dV, and we can assume that this must be a very tiny fluid element, but this tiny fluid element is going in a circle. You see that this is a part of a circle. So this tiny fluid must be going like this. Recall, recall, recall. Circular motion. What happens in circular motion? In circular motion, whenever a particle undergoes a curved motion, a curvilinear motion, it so happens that there has to be a force that acts towards its center. This force gives us the necessary centripetal acceleration, v square by r. V square by r is the necessary centripetal acceleration. Now you will find a lots of teachers and a lot of students making this mistake that they call it the centripetal force. But my dear students, there is nothing called the centripetal force. It's the centripetal condition that we're talking about. And what is the centripetal condition? That there has to be a net force acting towards the center. Let's get back to our fluid element. If this is going into a curve, then there must be a net force in this direction. There must be a net force towards the center. I mean, you get it, right? That the center is not on this side. The center is obviously that side. Okay. Now, if there's a net force over here, if there's a net force over here, then don't you think that there must be some static pressure over here? and there must be some static pressure over here, which would be acting upon these areas. Because this is a very tiny fluid element, we will assume that these areas are equal, which means that if the pressure over here is P, the force over here must be PA, where A is this tiny area. But we know that there has to be a net force this side. So this must be a greater pressure. So we will have P plus dP times A. So what's the net force towards the center, guys? What do you think is the net force? The net force is going to be P plus dPA minus PA, which is simply dPA. Now, what is this dP? This dP is the increment in pressure. Where is this increment in pressure happening? The increment in pressure is happening on this side, which means that if you go back to the problem, you will realize that the point 2 is at a higher pressure compared to point 1. All right? So we can say that if this point is 2, this point is 1, then we can say that pressure at 2 is greater than pressure at 1. Okay? Why am I emphasizing on this problem like this? Let me tell you the most common misconception that happens. So let's try to understand where students usually tend to get confused. They get confused in thinking that the fluid's particle that start from here, they come like this, they all travel parallelly. But then these guys, they turn like that. And the argument that I usually get from my students is that, sir, these guys are going to turn into a larger circle. Shouldn't these guys, the ones at 2, be going at a higher velocity because they are covering a larger distance in a small amount of time? But guys, what is the truth? The truth is that the pressure at 2 is greater than the pressure at 1. When the pressure at 2 is greater, so let's apply Bernoulli's theorem. So wherever the pressure is greater, we can say that over there, the speed of the fluid particle is actually less. Let me show you how. So assume that there is this point 1, there is a point 2 dash, and there's a point 1 dash. First of all, very first of all, you cannot apply Bernoulli's between 1 and 2. Why? Because 1 and 2 are not on the same streamline. If you want to write it in your notes, write it somewhere. You can only apply Bernoulli's equation on 2 points that are on the same streamline. And you cannot apply that on 1 and 2. But can you apply them on 1 and 1 dash? Yes, you can. So we can say that the pressure at 1 dash should be equal to the pressure at 1 plus half rho V1 square. What about the pressure at 2 dash? That should be equal to pressure at 2 plus half rho V2 square. But it so happens that they are both entering at the same point. So the pressure at 2 dash and the pressure at 1 dash have to be the same. All right, which is why I can equate these two equations. All right, because this is pressure at 1 dash, this is pressure at 2 dash. So I can just simply say that P1 plus half rho V1 square equals to P2 plus half rho V2 square. Please do not get confused about the equation of continuity and all that in this question. We understand that P2 is greater than P1, which we have already concluded in our previous slide. So we can say that half rho V1 square minus half rho V2 square is equals to P2 minus P1. So if this thing is positive, this thing must also be positive. And if this thing is positive, then this means that half rho V1 square minus half rho V2 square is definitely bigger than 0, which implies that V1 square is bigger than V2 square, or V1 is simply bigger than V2, because these are all positive values. So now we clearly understand that the particles at 1 are going faster than the particles at 2. Okay. Here, the particles are going faster in this question. Here. Now we come back to the original doubt by the students. The students, they ask me that, sir, the particles at 2, they appear to be moving faster because they are covering a longer distance. Now here's the thing. Nobody enforced these streamlines to go hand in hand. Okay, it's not gonna be like this, that the particle over here and the particle over here, they will always follow a path like this, where they are always moving with each other. Nobody made a law like that. Nobody did. That's not a law. This is no law that explains that these particles have to always be parallel to each other. They don't have to be. They don't have to be. What could happen is that the particles over here could just go very fast and the particle over here could be going very slow. So what would you say about the streamlines? Guys, the streamlines will look like this. I'm going to make it with a different color. So the streamlines you see will be more crowded over here and very less, they will be more crowded over here and they will be less crowded over here. This is very, very non-counterintuitive. The streamlines over here are less crowded. The streamlines over here are more crowded. So you can say whenever streamlines are more crowded, the speed is higher and vice versa. That's how it works. Whenever the streamlines are more crowded, the streamlines are closer together, you notice that there is a higher speed wherever they are more crowded. Okay, so this is going to be the shape of the streamlines. The most common wrong answer in this question is that the streamlines are like this. This is wrong. Okay, I'm just gonna, that's wrong. Okay, this one's right. Let's put a green on this. All right, so that's how it works. I hope you enjoyed the question, guys. This is a very beautiful, interesting question, and I hope the concepts were clear. Let's be more awesome. Let's go to the next problem. Very beautiful problem. I would like you guys to pause the video, read the question, and then I will explain. Pause the video, guys. Okay, so what's happening over here? We have two manometric tubes. Oh, what is that? A fancy word. Manometric tubes. You guys know what manometer is, right? You've seen the physics-rich fluid statics videos. You will learn what manometric tubes are. I have explained it in the statics videos. So, two manometric tubes are mounted on a horizontal pipe of varying cross section. And you see that these are the cross sections that the question talks about. This cross section, this one, and this one. These are the cross sections that the question talks about. And he's saying that these areas are A1 and A2. So, then he says, find the volume of water flowing across the pipe's section per unit time. It's a very long way of saying, find the volume flow rate. The volume of water across the pipe's cross section per unit time is volume per unit time. This is volume flow rate. Okay, so he's saying that the difference in water column is delta H. Now you see, guys, that if we draw our diagram in a nice clean manner, what you see over here is, okay, let me just zoom this thing. Yeah, so that I can show you the streamlines. What do you see over here? You see that liquid flows like this and then flows like that. Okay, liquid comes, flows like this and goes like that. Didn't we just study a while ago that if the streamlines are crowded, then what happens? The speed is higher. You see, they are the same streamlines over here and over here. But here they are more crowded. Here, less crowded. Which means that over here the speed is higher and over here the speed is lesser. I hope you understand this. So you see, guys, that I can apply Bernoulli's equation between this point and that point. Oh, you know what? If I should extend this, let's extend this. Let's go. These are all streamlines. And you see they are again less crowded. So what I can do is that I can apply Bernoulli's equation at this point A and at this point B. Okay? The point A and the point B. I should mark it on the same streamline. All right? Let's get back to our original size. Yep. So what's happening? We can say that the pressure over here is P1 and the pressure over here is P2. Okay, what kind of pressure is this? Why is there pressure? This is the static pressure, by the way. This is not the dynamic pressure, this is the static pressure. So these particles, they go, okay, and they only cross like this. They lose their whatever perpendicular velocity is. They lose that and they go and they cross like that. Which means that there will be some fluid particles that will be stuck over here. Over here. There will be some fluid particles that will be stuck over here. Let's just over here like that. And similarly, some fluid particles stuck over here in this region. Okay? In this region. So what's happening? Because these fluid particles are stuck over here, they are applying a downward pressure onto this flowing fluid. Okay, they want to come down, but the flowing fluid particles, they have whatever vertical velocity, they'll be like, don't come down. Okay, the particles in this, they want to come down because of gravity, but the ones that are flowing, they punch them up and they're like, don't come down. Which means that, how do we apply Bernoulli's over here? You see, P1 plus half rho V1 square is the expression for Bernoulli's over here, where we understand that this P1 is actually the pressure because of the atmospheric P0 and this rho G H1 and the water column, which is what I have written over here. Similarly, over here, what is the pressure P2? It's because of the atmospheric and this water column height rho G H2. And we have been given in the question that H2 minus H1 is delta H. So why don't we just simply subtract this? We can just simply say that rho G H2 minus rho G H1. We're subtracting this minus this minus this. That becomes rho G bracket H2 minus H1. I'm just going to write it as delta H. And that, my dear students, is P2 minus P1. All right. This is just P2 minus P1, which I can conveniently get from here. Okay. So let's go to the next slide. What was our Bernoulli's expression? It was this. Half rho V1 square plus P1 equals to half rho V2 square plus P2. And what do we have from here? We have P2 minus P1 is equals to rho G delta H. So let's do a little bit mix and match. Half rho V1 square minus half rho P2 square. This thing goes here. This P1 goes there. It becomes P2 minus P1, which is equals to rho G delta H. All right. Now, what do we have to do? We have to see that this rho gets cancelled. This 2 can go on that side. V1 square minus V2 square simply becomes 2g delta h. Okay. Before that wretched thought comes into your mind of applying v square equals to u square plus 2as, let me remind you, that's not what I have done. Okay, don't do that. Please, for the love of God, if there is a God of physics, please don't do that. V square minus u square equals to 2s is not what I've applied over here. Okay, this is come out of energy conservation, and energy conservation's consequence is the Bernoulli's equation. Guys, please, please. Okay, so v1 square minus v2 square is 2g delta h, does not come out of the third equation of motion, it comes out of energy conservation. All right. So this is one very important equation that we have. Also, we are looking for the continuity equation. Let me write the continuity equation over here. What is the equation of continuity? Equation of continuity is going to give us a1 v1 equals a2 v2. All right. It's going to give us a1 v1 equals a2 v2. What can we do about this? Actually, this is v dot. This is what we have to find. All right. We have to find the product of a and v. All right. So why don't we just put this over here and see what we get. Let's put this thing over here and let's see what we get. We get v1 square minus, now I'm going to put v2 as a1 upon a2 times v1. So let me just put v2 equals to a1 by a2 times v1. Put here a1 upon a2 times v1. It's a square, so I've given it a square. So this is a 2gh, delta h, I'm sorry, delta h. Take v1 common, actually v1 square is common. So v1 square is 1 minus a1 by a2 square, that is 2g delta h. All right. I will just remove this part because we have no use of this part as of now, and we'll put this part over here. So what do we have? We have v1 square equals to 2g delta h upon 1 minus a1 by a2 the whole square. Or we can say, taking root on both sides, v1 is simply 2g delta h upon 1 minus a1 by a2 the whole square to the power of 1 by 2. Please notice that I could have written this as a whole root like this and like this. It's the same thing. I find this raised to power 1 upon 2 more convenient to write. And what exactly am I looking for, guys? I am looking for the volume flow rate. That's how I represent it, v dot. This is going to be simply a1, v1, and then you can just take this value, zup, 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 over here, multiply this with a1. Having a smart board is so cool, man. Guys, this is it for now. I'm going to be back with more Awesomeologist questions on the same concept. Until then, you guys know what to do. Oh, by the way, I just want to show you that there are more questions over here. There are more questions and we have so much to do. So much to do. So stay tuned and get physics rich.